Thanks. So I'm Vinny Monaco, and this talk is about keylogging side channels. So this is an SoK, so there will necessarily be a lot of material in the paper that's omitted from the talk. So to start, I think it's worth reviewing what goes into a keystroke. And when I say keystroke, what I'm referring to is the complete action by the user of pressing or releasing a single key on a physical full-size keyboard. And within that action, we may commonly refer to two discrete events, the time of actuation or key press and the time of deactuation or key release. So there are about a dozen or so major components and facilities that work together to enable textual input. Later on, I'll talk a lot about the timing of a keystroke, so it'll be important to keep in mind how each component introduces a delay or variability to that timing. So to start, the user introduces a physical delay. This is the time it takes the typist to position their hands and fingers over the keyboard, which depends on the behavior of the typist and on physical characteristics of the keyboard, such as key type and travel distance. The keyboard itself is responsible for sensing and digitizing the keystroke. This is typically performed through conductance, so pressing a key closes a circuit. And the key circuits are arranged in a matrix layout, so the microprocessor in the keyboard will sequentially activate each column of the matrix and then sense any keys that are pressed by detecting which rows become active. And then when a key press is detected, it'll then enter a subroutine to encode and transmit that event to the host. On the host, an interrupt is raised. There's a delay from the time the interrupt is raised until it's acknowledged and passed along to whatever application is waiting for text input. And this delay depends on the process scheduling and preemption policies of the host. And then finally, if we consider a web application where the role of the client is to relay user input events back to the server, then from the perspective of the server or another host on the network, we have the usual delays associated with the network. And so looking at this complete picture, a keylogging side channel by definition then is some method to determine what the user typed by leveraging an unintended information source. And typically this involves leveraging some component in this pipeline beyond its intended functionality. So keylogging is composed of two separate problems, detection and identification. In detection, we're just interested in trying to establish the presence of a keystroke within some finite time window. So this is a binary classification problem. And this generally becomes more difficult as the size of the window decreases. So for example, I could, with pretty high confidence, say that a person in this room pressed a key within the past hour, but that does little to tell me which key that actually was, which brings us to the second problem, which is key identification. In this case, given that a keystroke has occurred, we then try to determine which key that was, which key on the keyboard the user interacted with. And being a multi-class classification problem, we may look at a classification accuracy or information gain to judge how well our method works. So keylogging side channel attacks actually have a pretty rich history. Going back about 75 years, we can see the Tempest threat as one of the first demonstrated keylogging side channel attacks. So this occurred when Bell Laboratory researchers discovered an electromagnetic spike emanating from one of their teletype terminals. And this EM spike pretty reliably enabled plain text recovery. So this discovery evolved into the Tempest threat, which grew to cover other modalities such as acoustic and seismic, although it's not really known how well those modalities worked around that time. And then about 30 years ago, we had one of the first keylogging side channel attacks discovered in the wild. This occurred when a hardware device was discovered inside the IBM Selectric typewriters at the US Embassy in Moscow. So it turns out that the Soviets had developed this rather sophisticated device or hardware bug that they implanted into the embassy typewriters through a supply chain attack. And this device sensed which keys were pressed through the motion of levers inside the typewriter and then relayed this information back to a nearby listening post through radio bursts. And so this attack went on for about 8 years or so until it was discovered. And Project Gunman was the U.S. response to mitigate this threat by replacing all the equipment at the U.S. Embassy they thought might be affected. So keylogging side channel attacks today are relatively more sophisticated. They've grown to cover dozens of different modalities. I think this is due to a combination of both ubiquitous sensing along with the advancement of machine learning and signal processing capabilities. So there's too many to go into detail on every single one during this talk, of course, but looking at this cartoon, I would just like to highlight some of the major attacks that have been developed within the past several decades. So we have attacks targeting the user behavior. Typically this involves sensing the hand motion of the typist, either with line of sight to the keyboard, looking at video, or the acceleration on a smartwatch, or through Wi-Fi signal distortion. We have attacks targeting the keyboard, looking at the local emanations of the keyboard, either the acoustics or seismic activity. Similarly, we might look at either radio or parasitic capacitance, which might carry the unencrypted USB or PS2 signal over power lines. We have attacks on the host, looking at things like CPU load, cache usage, or the proc file system to detect keystrokes. And then finally, considering a web application or some other distributed application where the client is relaying user input events back to the server. If we look at the timing of the upstream traffic, which might reveal the timing of the key presses, that in turn can be used to mount a temporal keylogging attack. And then similarly, the downstream traffic if the server is generating a unique response to each keystroke. We have this taxonomy that I developed as part of this work that characterizes each attack along roughly 5 dimensions. I'm not going to go into detail on every single one. I would like to focus on the one that I consider to be the most interesting and important, which characterizes how a keylogging side channel actually leads to keylogging, which could be by leaking either spatial information or temporal information or a combination of the two. So a spatial side channel is one that's giving us either the key locations or the key distances. And for lack of a better term, I refer to these as first order and second order spatial side channels. So a first order spatial side channel is one that's giving us a coordinate or location on the keyboard. So if we have, using acoustics as an example, multiple microphones positioned around the keyboard, we might use the time difference arrival method to try to localize the sound source of a keystroke. In this way, we learn a coordinate or a location on the keyboard. A second order spatial side channel, on the other hand, gives us only a relative distance between keystrokes. So imagine we now only have a single microphone next to the keyboard. We might look at the acoustic waveform of different keystrokes, and we'll actually see that if those keystrokes occurred on the same key or on keys that are close by, they'll sound more similar to each other than keys that are far apart. And this is due to a kind of drum effect by the keyboard. However, in this way, since we're only learning relative distances between keystrokes, we can end up with an isomorphism between different keystroke sequences that have the same or very similar distance matrices. But it turns out that if we consider a natural language such as English, as the length of the sequence increases, the number of isomorphisms decreases, and the information gains that we can achieve in a second order channel actually approach what we would get in a first order channel. So temporal keylogging side channel, on the other hand, leverages only the timing of a keystroke, typically either the key press or key release timing, to determine what the user types. And this is generally possible due to 2 factors. The first is there's a temporal dependence on what was typed. So the timing of a keystroke depends on what was typed. So in this figure, looking at the key press latency, the time between successive key presses versus the inter-key distance, the physical distance between those keys on the keyboard, we see that the keys that are far apart are actually pressed in quicker succession than the keys that are close together. And so this is because the typist, especially the touch typist, is able to process those keys that are far apart in parallel with alternate hands and fingers, whereas the keys that are close together require the typist to reposition their hand and finger, which takes a little more time. So the second factor that enables this is that this behavior is the same for different users. So in this figure, looking at 2 different users, we see this very similar inverse scaling relationship between key press latency and inter-key distance. So it's this temporal dependence and the similarity in behavior among users that would enable us to carry out an attack like this, where we may, say with ground truth, with known keystrokes with associated timestamps from an independent data set, infer what another user typed based only on the timings. However, if we look at the performance of such an attack, we'll see that this actually varies quite a bit among users. And we actually end up with a situation kind of reminiscent of the biometric menagerie, which describes the performance of a biometric authentication system, how this works well for some users, not so well for others. So in this figure, looking at the information gain, or the average number of bits gained per latency for each user, we see we have a range in performance and attack success among users. So in the biometric menagerie, The lambs are those users who are easy to impersonate, and in our side channel attacks, the lambs are those users who are relatively vulnerable to attack. So we can gain a lot of information per latency. And in a biometric system, the goats are those users who have difficulty authenticating as themselves. So they have low genuine match scores. And in our side channel attack, the goats are those users who are relatively resilient to attack. So it's actually good to be a side channel goat. And it turns out that there's actually a correspondence between the biometric animal types and the side channel animal types. So if you're a biometric goat, you're likely also a side channel goat. So I have a poster that examines this relationship in more detail. So if you're interested, you can come find me during the poster session this evening. So coming out of this work, I think there's first one very broad observation that we can make, and that is that behavior homogeneity, to a certain extent, is an indication as to the severity of a side channel attack. So the semiconductor fabrication process is very tightly controlled. We end up with devices with highly reproducible behavior. So when a timing side channel attack is developed for a particular CPU, it's expected to work for other physical devices of the same make and model. Whereas we have much more diversity in human behavior, and this diversity is what enables biometric identification, but to an extent, it's also what accounts for that range in performance in our temporal keylogging attack, where the attack works well for some users, not so well for others. So not everyone's a touch typist. We have hunt and peckers and combinations of different typing styles. So the side channel attack that's targeting user behavior may exhibit this range in performance. So to an extent, the similarity in behavior among a population of users or a population of devices is an indication as to how vulnerable that population is to a side channel attack. And now, as we begin to consider behavior heterogeneity and behavior homogeneity in a common framework, we can begin to examine the relationship and possible trade-off between these two factors. Robert Langlands is a well-known mathematician who just recently was awarded the Abel Prize, which is like the Nobel Prize in mathematics. And his vision, called Langlands program, was to develop these links between the different branches of mathematics in such a way that enabled new techniques to be applied to old problems and revealed some really fundamental relationships between the different branches of mathematics. So this was a really revolutionary idea at the time. In the same spirit as Langlands program, I envision reasoning about the information a channel might leak about a user's identity, along with the information about what actions that user performs, so what keys they press on a keyboard. This, in turn, I think may enable us to begin to identify scenarios where we have a possible trade-off between these two factors, possibly where we have to choose one or the other, or some type of continuous scale, or maybe neither. So to summarize the main points of this talk, we've seen keylogging side channel attacks advance considerably over the past 75 years. This work was an attempt to consolidate some of that knowledge and act as a jumping off point for future work in this area. Moving forward, I think it'll be important and beneficial to consider those similarities in behavior and differences in behavior in a common framework and begin to examine the relationship and possible trade-off between these two factors. And finally, I'll end with a prediction, which is that I think the performance of temporal keylogging attacks is going to improve in the near future. So I say this considering the abundance of client-server applications where the role of the client is to record user input events and relay these back to the server in near real time. If we look at the timing of those events, what information can we determine about the user's identity or actions? There's certainly a limit to the amount of information I think we can pull out of those timings, but considering that from what I've seen, state-of-the-art machine learning techniques haven't yet had a chance to feed back into this problem, I don't think we've reached that limit yet. So that concludes the talk. Thank you, everyone, for listening.
Okay, always a scary talk. Whoops, am I on? Okay. Again, any questions, please come up to the mic. I think I see a couple people going to the, oh my gosh.
Hi, Kevin.
The Russians. I know you. Okay, go, name and affiliation, please.
Yes, of course. Robert Lucho from MIT Lincoln Lab. So I'm just curious, Does the layout of the keyboard have any effect or significance in any of the work that you've seen?
It does. So
So, for example, the Dvorak.
yeah. So
Okay.
an attack. So the layout, it does have an effect because ultimately it's going to affect how the user's typing on the keyboard, the user
Right.
behavior. If you're learning distances between keys on a keyboard, you may have to then go back and correlate or find a correspondence between those distances and your actual mappings between keys to physical keys. Unfortunately, there aren't enough Dvorak users, if only there were more of us, to try to evaluate the performance of such an attack, but they're relatively sparse. I think it would be beneficial to look at, for example, regional layouts, for example, US versus European based, which there are data sets available to look at something like that.
Okay, thank you.
All right. Before Robert goes, since I haven't seen Robert for about 10 years, and you left a Russian doll in my office, I just want to know, are you still getting a good signal?
I can't tell you.
Okay. I haven't seen this former student for years. Okay, others at the mic. Okay, I have one question before we wrap up then, and that is, you know, there are all sorts of new form factors of keyboards, you know, of course, smartphones and such. There was the gyrophone paper from a few years ago that used sensors. What are some of your thoughts about some of these new, well, relatively new UIs that are becoming popular?
Yeah, so unfortunately, I didn't cover mobile input in this work just because I couldn't fit it all into 18 pages. I would have liked to. I think that the user behaviors we see are relatively much more diverse. So it's not just a matter of you know, touch typists versus hunt and peckers. We have, I think, a much wider variety of user input behavior on a mobile device, especially a soft keyboard. And so then we've seen attacks that are leveraging modalities that you might not have in on a physical keyboard, such as the iTel paper, looking at eye movement. So you don't get that kind of behavior, or at least for a touch typist, you're not looking at the keyboard. So it opens up new attack vectors and possibly more attack vectors, since you're now co-located with the device that's sensing and recording input.
Okay, maybe a future paper. Okay, well, let's thank Vinny. All right, thank you.